Hello, operating systems people. This is Gabe again. Today, we're going to talk about system design and specifically the implementation considerations that you have to make when you are programming systems. So, what do these include? Why are systems different than applications? So, when designing and implementing an interface for a system, what do we need to consider? And let's kind of dive into a little bit as to why systems are slightly different than applications so that we can understand the core of the argument. So, one, there's asymmetric trust when you're communicating between a system module and a client. Asymmetric trust simply means the application essentially trusts the module. This is maybe hand waving a little bit, but the module certainly does not trust the application, right? If we're talking about, for instance, user level and kernel level, the kernel does not trust the application. So you have this notion of asymmetric trust. It's not as easy as just writing normal code in your application or interacting with a library. And one of the implications of this is essentially that you have very limited pass or return by reference. So if you want to pass a pointer across the module boundary, well, you need to be really careful because the kernel, for instance, might not want to access that pointer directly, right? So you have to be very careful. Certainly, if you have a pointer within the kernel, you don't want to pass that up to user level because, hey, user level can't access the kernel. So when you have this asymmetric trust, you need to change how you think about pointers and integrate that into the system. Certainly, system-level modules serve multiple clients, and this simply means that their data structures have to represent that. Often this means separating the data structures into different pieces that are specific to the clients, which is, again, more complexity and something additional that you need to actually design for. System-level modules also need to multiplex resources. If they are controlling resources and providing an abstraction for accessing them, well, they have things like non-functional concerns. If you're a scheduler managing a CPU, you are managing a non-functional resource, which is the CPU. So you're dispatching between different threads. Applications typically don't need to worry about this level of fidelity of system interactions. And of course, you need to interact with I/O almost directly, right? If you are the disk driver, you're interacting with it just right in your face. You are the one interacting with it, doing DMA, interacting with interrupts, etc. Even the file system low, of course, needs to interact with I/O. So concurrency is a pervasive concern that you have to consider. And then finally, on multi-core systems, you typically have to worry about parallelism. And though it's nice that we can write applications that run in a single thread and don't need to worry about parallelism, the system doesn't really have that escape hatch. If it wants to be able to run applications that can use multiple cores, it itself needs to use multiple cores. So systems and system modules are different, and they have a number of constraints on their interfaces that I'm going to go through now. The first one, and this is the biggie, is the naming of resources. So I'm going to be talking about resources in a very abstract sense. These may be threads, they may be memory pages, they may be files, they may be pipes, etc. Any type of a abstract object that an operating system is providing for you, I'm going to call those resources, right? They are the resources that the module is providing the abstraction of. So the server module provides these, right? In the picture on the right, you see these as the purple circles within the server and the client up top. So the client module needs to refer to those resources in some way. If they are providing file operations, then they need to be able to refer to the file that they're trying to perform an operation on. That notion of being able to name one of the resources is fundamental in how we design system modules. Now, names can take many, many forms. They could be a path in a hierarchical namespace like we're used to in the file system. They could be relative paths like foo. They could be hierarchical and relative paths, foo bar. They could be absolute paths like home gparmer foo. Or we could even be talking about things like the internet where URLs include www, which is the domain portion, and then, the U bar and whatnot that are specifying the resource that you're actually accessing on that server. Names could be much more primitive than that. They could be integers. So a file descriptor is a name for a file that has already been opened. And we'll see that capability IDs are a more direct way to do that for all system resources. Names could be as simple as addresses as well, right? So when we are accessing memory and doing loads and stores, we are naming the chunk of memory that we want to access with the operation of either load or store and trying to actually modify that resource. And of course, this is virtual memory, and there are modules within the kernel that provide that notion of virtual memory. So, how do we think about naming? Well, the first thing that we need to think about is name resolution. So we have the client up top. In this case, it's Penny. She wants, obviously, to access the resource for ARF. And we need to, as the server module, somehow resolve that resource that Penny is naming as ARF to the actual resource within the component. So we can think of name resolution as just a function R that takes the name and returns some sort of a reference to the resource. Again, the references get a little complicated. This is already a little bit of a lie because it's actually something like this, where the function R, the resolution, would take the name and some sort of a PID, because every single client might have a different name for different resources. And of course, you can think of this as the file descriptors of different processes mean completely different thing. File descriptor 2 in one process might be completely different from file descriptor 2 in another. Same for addresses, because hey, we have different virtual memory regions that we execute in. And I do want to point out here that obviously PID stands for PUP ID, not process ID, just so that we all understand each other. So what does this graphically look like? Well, Penny says, I want to access the resource ARF. So she passes it to the resolution function within our server module, which then figures out somehow in its own implementation which resource that refers to, and it creates what's called a binding to that resource. So resources are bound to specific clients, and we can see here the client has resolved two resources that are now bound, and those binds are referred to with the arrows here, right? So if these two modules, the client and the server, share memory, so they're in essentially the same virtual address space, that means that they can share these references as pointers. So you might imagine that the server below simply returns some sort of a pointer up to the client, and the client can pass that pointer into future operations it wants to perform on the resource. So in this case, they're pointers because they're in the same address space effectively. They share the memory namespace. Therefore, we can pass by reference. Now, of course, that provides no isolation whatsoever. So if we want to provide isolation, which is the dotted red line here, then we can't share pointers between the client and the server because the pointers don't mean anything if they can't be dereferenced appropriately, right? And isolation means that we have essentially disjoint sets of memory that the client and server are accessing. Therefore, any pointers that are shared when dereferenced would fall in the best case, right? So, in these cases, we use handles. And handles are usually just some sort of an integer. It might be slightly more complicated than that. Over the web, we have cookies that track kind of our sessions, right? A session is effectively a handle to the resources that we have persistently. But these handles, effectively, these integers, are passed from client to the server, and now the server has to implement a function f that maps between those handles to the corresponding resources. Note, logically, the resources are already bound to the client. It's just that we have to do a little bit of dynamic work to implement that binding. This notion of dynamic binding is very common and is used to implement things like the file descriptor table, right? When we do a read call or a write call, we pass a file descriptor, and that file descriptor is looked up in a file descriptor table. That is essentially the function f that is displayed here in yellow. So the example here is that name resolution in Unix of arf is done with the open call, and that returns a handle, which is a dynamic binding to the file resource that refers to. And then we can operate on that bound resource, on that handle, using, for instance, the read system call, right? Now, there are a couple of really cool things about this notion of naming that's very powerful, and I want to point out a few of them here. So now we see on the right we have two clients that are isolated from each other, and the server is isolated from them. And now we have two functions, f and f prime, that provide mappings each for the clients, respectively, right? So each of the clients now has their own way. The server module provides a specific way of providing those mappings from the handles to the resources to different clients. And you can see on the bottom that we have another client. I'm sorry, I know it's graphically below the server, but you can see the direction of the arrow. It's a client. And because it's in the same protection domain as that server, well, it can use actual pointers. So it can use kind of bindings by pointer. So you can see that even though we have one server, we could actually use different binding methods, assuming that that server wanted to implement both. But let's get back to f and f prime. It's really interesting because now we can look at the set of resources that are bound to a specific module, so client 1 or client 2 on the left or right, and those sets of resources define all of the accessible or modifiable resources from those clients. And we can start to say very specific things about isolation within the system. Disjoint sets for those resources essentially mean that at this point in time, those two clients are completely isolated from each other. If they cannot modify shared resources, then they can't impact each other, short of crashing the server module, of course, which here we're assuming doesn't happen. If there's an intersection between the two sets, then we have shared resources between the two clients, and those two clients might be able to impact each other, for instance, using IPC, passing data between each other, using those shared resources. So we can start to say very specific things about the isolation of the system if we simply think of these resolution functions, the bindings, and the different sets of resources that they make accessible. Okay, so this is all that I really want to go into names. It's a very, very deep issue, believe it or not, but I want to be able to get to some other stuff, so I'm going to move on. Once we have names and we have these bindings or these handles to be able to access different resources, the question is, what should the interface be that uses those names and bindings in some interesting way? And again in this class, we're going to come back to kind of a very typical example of this, which is the Unix Virtual File System interface, the VFS interface, which we're going to talk about quite a bit. And many of you have probably seen this. This is kind of open, read, write, close, create, unlink, kind of the normal types of APIs that we use for modifying kind of virtual objects within what we think of as our file system hierarchy, right? Now, what's interesting is that this is an interface that all Unixes implement in some way or the other, but below it, we have multiple different implementations of this interface. As I said in the last lecture, we have a polymorphic interface that's used by multiple modules or implemented by multiple modules. So these are replaceable depending on what part in the namespace, the hierarchical namespace we're accessing, we will actually be routed to a different module. So this is a resolution process. When we want to access a certain path within our namespace that actually identifies a certain module that will implement the VFS interface for the resources contained therein. So for instance, /proc is handled by the proc file system module. Sys is the sysfs module. All of the devices are in dev, so they all have their own device drivers that implement their VFS hooks. And then we have things like home, gparmer, etc., which is our normal file system, right? And that's kind of your file systems implementing those modules. So we see on the right in the diagram, we have that one interface implemented separately by the different modules of proc, file system, the device file system, etc. And those different modules implement that same interface to make all of the operations look the same. So the shell looks the same because, hey, the shell uses open, read, write, close, create, unlink, right? So now we have this nice uniformity in our namespace for how the system behaves, but we have the ability to modify the implementation willy-nilly. So this is really cool. We will see that Unix actually doesn't take this idea far enough, thus yielded the idea of Plan 9, which we'll talk about a lot later as well. There are variants on this API, this notion of kind of create, read, write, and delete is pretty universal. And in the book for the class, I kind of outlined some examples for CRUD, which is kind of, basic web interfaces. Create, read, update, delete, and SQL, etc. So this is actually a pretty uniform interface used in a lot of different contexts. Okay, so we've talked about names, we've talked about the power of names and how we integrate them into our interfaces. We talked about one example of how we choose kind of an interface that can maximally interact with this namespace and have different modules that are resolved to for different areas within that namespace. Now the question is, what data do we pass over that interface? And I'm going to go over a few examples here. And I'm going to call this the resource data representation. How do you actually represent the data that is streaming over that interface in some way, right? In the VFS API that we just looked at, if you think about read and write, well, for read and write, you're really just passing a bit stream of untyped data over it, right? Untyped means that, none of the bytes that we're passing over read and write really differ from each other, right? They're just data. Types basically assign some sort of semantics to clusters of data, right? You could think of structs in C. Unix doesn't have any of that. It doesn't type its data. All of the data passing over read and write is just an untyped bit stream of data. On the web, we typically think about passing data back and forth in some sort of a format. For instance, JSON is really popular, right? There are 10,000 other different formats, but you can think of JSON as being one of the data representations that's the core of the internet, right? We pass arguments by formatting them as JSON. We can pass entire media files by encoding them in JSON, right? This is a fairly uniform way to actually pass data on the internet and communicate between different modules. Languages also think in terms of modules, right? Java thinks in terms of, okay, I have the JVM and then I have these libraries off on the side. How do I communicate with those modules, which are separate? How do I communicate with those libraries that are separate modules? In the Python world, you have a lot of different things going on in terms of libraries and different languages and whatnot. But all languages essentially speak in typed structures. And if we want to communicate with libraries, then we might need to serialize and deserialize our type structures into a representation that the other language can understand. But in essence, within a given language, we like to think in terms of types. So you can really think about language-based communication as being, in some sense, kind of the structured alternative to things like the bit streams that Unix uses. We'll see that later adding this structure has a lot of benefits, but also, of course, some downsides. Okay. So we talked about naming, how naming can be very powerful, especially when you have uniform ways of performing operations on the resources involved. And we talked about different ways that those resources can effectively be communicated with, the data representation that we use to kind of communicate with generic resources in Unix, for instance, hidden by the VFS layer. Now let's take a little bit of a detour and talk about optimization, because there are a couple of optimizations that are just so part and parcel for system modules that it would be a little negligent for me to not go over them. These are really, really common. So the first one that I want to go over is data aggregation. And the idea here is that when we want to pass data between two isolated modules, then we can often make that communication more efficient by trading latency. How do we do that? Well, if we think that each operation that we're going to perform, so let's say a read, right? User level is isolated from kernel level. So a read call through the VFS needs to take the data that is being read from the kernel and somehow pass it up to user level, right? The read operation itself takes some amount of time, here represented as the boldface italic T, right? So to read one file, for instance, it takes T, right? However, there are some communication costs here. System calls are not free. You can think that system calls at least have an overhead of 100 cycles. For reading an extremely small file in a very fast kernel, you can imagine that would be a pretty significant cost. But there are also times when we think we're reading from a file, but actually we're reading from a pipe. So it's actually IPC, inter-process communication, that's being done to actually carry out the read. Well, now we're talking on the order of 5,000 cycles, right? So there are communication costs in addition to the cost of the operation itself that need to be represented. And we call these, it should be C here. So it says O here, but it should be C for costs, right? So think a little bit, what are examples of these types of communication costs? I went over two. Can you think of any others? Pause it, come back. Penny is waiting. She's very eager to hear your response. So I went over two. System calls are one of those costs. Inter-process communication, IPC, is one. Remote procedure call is another one. This is actually communicating over the internet, not just locally. You can think of these as like AJAX, asynchronous calls to web servers. You could think of it as other things, middleware calls, whatever. Remote procedure calls in general. And these costs, in general, are kind of a function of the isolation that we provide, right? System calls are relatively fast. They aren't zero overhead, but they're relatively fast compared to the others. But, the isolation is somewhat limited. The client, for instance, has almost no isolation from the kernel. So we have this asymmetric type of isolation. For IPC, it's a little bit different. We have two clients that are streaming data from the other, but, neither of them can really crash the other trivially. For RPC, we're increasing the isolation by going over a network. Now, the communicating node can fail completely, and it's not going to impact the other thing on the other side of the internet, right? So these costs are essentially some sort of a complicated function of isolation within the system. Now, if we think about the costs of performing an operation now, it's T plus C, right? Now, if we make N requests, then of course it's N times T plus C, right? Just pay that cost N times. The whole idea behind the optimization of data aggregation is just that we aggregate a whole bunch of data together and send it all as one batched set of data, therefore attempting to minimize the communication costs. And in the extreme case, if we have an N request and we're using this notion of batching, then we still, of course, need to perform N times the cost of whatever functional operation we're performing. Reading from a file was my previous example. But we might only need to pay that communication cost once. So we're essentially batching up and saving data and then transmitting it all at once to try to save in those communication costs. Pipes are engineered in this way. Pipes for inter-process communication are essentially a bounded buffer of some finite size. We can write a byte into it, and just because we've written a byte into the pipe doesn't mean that we're going to switch processes and go over to the other one yet. We might write another byte and another byte and another byte, and only after we've written enough bytes to fill up the pipe's buffer in the kernel will we switch over to the other process. Unless, of course, the kernel decides because of scheduling to switch sooner. So this notion of batching is fairly, it's baked into a lot of asynchronous operations. So I just want to go over the example again. If we're batching data, then we might in-queue requests from data instead of performing the operation immediately. After we've in-queued n of these requests for some n that we might engineer into the system, we perform that operation on all of them, right? We pay the communication cost and try to perform the operation on each of them separately. However, there's a risk with this. If we're waiting until there's n data to actually, before we actually ask for the operations to be performed, well, what if we never get n requests, right? Then we never perform any of the operations. That's a problem. So you often want to associate some time as well with this. Either if we receive n requests, then we'll perform n of those operations. Or if 10 milliseconds have elapsed, then we'll perform however many operations are pending, right? So this points out that this really trades the notion of latency for throughput. We get better throughput because we are minimizing costs within the system, which is better using the cycles of the system, therefore doing more work, therefore having higher throughput. However, we're sacrificing latency because there is some cost for queuing up these requests, right? If we end up queuing up the requests and then sending them out 10 milliseconds later, then that first request that we would have made immediately, we're essentially delaying for 10 milliseconds. Therefore, we are trading latency for throughput. So you don't always want to do this, but you do often want to do this. So I went over the Unix pipes as an example here, but printf is another example that might be surprising to a lot of people. I believe that the default implementations of printf will actually not print out until you try to print a new line character. So if you want printf to always print out, then you actually need to call flush to tell it to actually print out that data that you've asked it to. So if you just print a relatively small amount of data without a new line, it might batch that forever and never actually print it out, right? But printing is very expensive and the system call is relatively expensive, so we want to do batching to avoid that communication cost. We also think about aggregation in another dimension. So another optimization. This is the notion of action aggregation. This is quite a bit less common, but it is important to think about it. This is kind of the notion of moving your computation from where your client is to where the data is. So you often want to think of it in those terms. And the idea here is that the communication costs might be pretty significant again. So if what we could do is move the computation to where the data is, then all of a sudden you don't need to pay the communication costs really at all, because the computation is being done somehow where the data is in the server. Right? This hopefully sounds horribly dangerous and precarious, because somehow we're doing like client computation in the server module. How could this be isolated? How could this be trusted? So usually we only execute interpreted code in this way. So somehow we maintain isolation in that server module by only executing code that we are limiting. It cannot access arbitrary memory within the server. So the extended Berkeley packet filters, eBPF, are small little programs that you can actually upload into the Linux kernel. So you can write programs that will execute when certain operations are performed within the kernel. Databases have stored procedures, which is essentially the idea that you can put your SQL into the database and execute it repeatedly there without your interaction. This one's a little weird, but I wanted to include it because it's a little bit more novel. GraphQL is a JSON format that allows you to perform multiple operations on a web page instead of making multiple operations one after the other using CRUD or REST operations. So Google that if you want to know more, but it's pretty cool. And it allows you to essentially filter and transform website data within kind of the GraphQL specification instead of by making multiple requests with your computation on the client in between. OpenGL and kind of video cards used to have, they're much less common now, but display lists. And this was kind of storing a bunch of graphical commands in the graphics server so that they could be performed quickly instead of having them in your client. JavaScript is almost a weird way of doing this as well. You could think of JavaScript as getting uploaded onto a client and executing there, as opposed to having all the computation be on the server. I didn't have it here because it's a strained analogy, but this notion of moving your computation to the data is not all that uncommon, and it is another way to actually kind of minimize communication costs, but it often comes at a huge cost, and that's that it makes it really, really complex. Your server module just balloons in complexity because you need to effectively enable interpretation of a full-blown computer programming language within your module, and it needs to consider security as a foremost design because the client might be malicious, right? It also trades agility, and agility is this idea that how quickly can you change your code in response to new feature requests and things like that. Once you open up your program to kind of all of these APIs of a general programming language and an interpreted language, then it makes it often much more difficult to change your implementation because you have a broader API to that programming language. So these are two optimizations that we often consider when we're designing systems. And you can see they're in some sense integrated into the VFS because everything that we talked about, pipes and whatnot, are kind of leads implemented, at least kind of data aggregation implemented with behind that VFS layer in pipes. Okay, now the big two that drive a lot of complexity in system applications, I'm actually not going to go into either of them much here because we're going to talk about them throughout the entire semester. One of them is concurrency. And this is simply the idea that the client and or portions of the service, of the server module, will probably have to wait in some sense for some event to happen in the future. So we're talking about systems here. So systems means, you're probably interacting with disk, you're probably interacting with network, etc. So you're probably going to have to wait for some non-deterministic amount of time until that I/O completes, whether you're reading it or you're writing it, right? If you're doing communication, if you're implementing pipes in some sort of a VFS module, you are inherently concurrent because you're going to have multiple clients making requests for interaction between those clients, and you're going to have to be waking up and sleeping those clients. And the ordering of all of this is completely non-deterministic, basically dependent on interrupts, be it time interrupts for when you're switching between different clients, or be it I/O, right? Oftentimes, system services, so some modules get so complicated that, they're massive and they might themselves have concurrency within the implementation. So if you have multiple threads within your module, they need to interact in some way. So now you need to do concurrent programming within that module. So concurrency is really just based on this idea that we have non-deterministic interactions that required controlling, blocking, and waking in response to requests and events, right? Okay, so how do we think about concurrency? There are two high-level ways to think about programming for concurrency in systems. One of them is event-driven architectures, the other is threaded architectures. Event-driven architectures fall under this idea that you want to execute some function. So you want to make a request, right? I want to request I/O, I want to request IPC. And you want to execute some function that you provide as an argument to that request when that request completes, when an event is triggered that says that that request has completed, right? So this is essentially saying, do this request and execute this thing when it's done, right? So we see this in JavaScript pre-2017 with promises, await, all of that stuff. You'd have code like is shown here. You might want to set some timeout, which is to say I want to wait for some sort of a non-deterministic event in the future, which is essentially waking up, in this case, 1 second into the future. But I can't block. JavaScript doesn't block. So instead, what I want to do is execute some function a second until the future, and I pass that function in as a closure. So what this code will do is essentially call the handle alarm function a second into the future, right? So this is event-driven architectures. When an event happens, execute some sort of a closure, which is a function with some data, right? libuv is a library that you're going to read the code of, and it's the foundation of Node, which is a server-side JavaScript implementation. Nginx is probably the most popular web server out there, and Nginx is an event-driven architecture, which means the entire Nginx web server, it isn't necessarily multi-threaded. It is for multi-core, but that's not but otherwise, if you're only on a single core, it would want to execute with a single thread. And these typically use completely non-blocking APIs because, of course, if you only have a single thread, then you can't block or else it won't be able to continue execution. So they use completely non-blocking APIs and execute these closures in response to the events happening within the system. For instance, on Nginx, a new client making a request. In contrast, we have threaded architectures. And threaded architectures are based around the idea that we can block a thread until some event happens and then resume the thread. So you kind of look at the execution of the code and you see a read to the file system. And that read may be blocking, but we don't really need to write code in a way that kind of, changes because of that. Instead, the thread just blocks. However, if you want to continue to use the CPU while that thread is blocked, well, you have to have a separate thread that can continue executing. Therefore, these blocking APIs end up giving us these thread-based architectures where the client wants to keep executing and use CPUs effectively, in spite of these blocking APIs. So there's kind of this notion that we have asynchronous APIs on the top and blocking APIs on the bottom. And threaded architectures include pthreads in Unix. RTOSes are typically, real-time operating systems are typically threaded for different reasons. And that's because we want a thread to be able to wake up and react to an event immediately. In event-driven architectures, you typically need to wait for the previous event to finish processing before you execute the next one. So both of these have a single problem and a single kind of challenge that they present. And that's essentially the question, how can I block awaiting a number of multiple events? So if I have 10 different network clients that I'm communicating with, and I want to block waiting or wait for an event in a non-blocking event-driven architecture on any one of those clients, how do I do it? Read doesn't let me do that. If read is blocking, then I can block waiting for a single client. If I used only non-blocking reads, then I could iterate through the 10 clients and just kind of have an infinite loop going through the 10 clients, waiting till one of them has some sort of an event. But that's polling. That's just actively trying to get new data, and that's not CPU efficient, right? So if there is nothing, we want to block. But the second that there's some event on any of the clients that we're waiting for, we want some sort of a notification. So this is the idea of an event multiplexing infrastructure, an event notification infrastructure, right? So epoll is a Linux version of this. FreeBSD has KQs, and select and poll are the traditional POSIX versions of this. So you can look up these system calls, read the man pages. All that they really do is take a number of file descriptors and block waiting for an event on any of them. Once any of them has an event, they will return which file descriptors had events so that the user level process can process them, right? Okay, so why am I talking about all of this, right? This notion that we have blocking or non-blocking APIs, and we have clients that want to use CPUs efficiently, effectively means that we have to deal with concurrency within our server modules. We need to figure out how to either block or not block different clients, and we need to provide facilities for those clients to be able to do event multiplexing if there are multiple resources that they might want to do computation on. This is really unavoidable, and it adds a ton of complexity to system level modules. The last thing that I want to talk about, and I'm going to do it very briefly because the third main thrust of this class focuses on this, is that, of course, you need to consider parallelism. And all that I'll say right now is that system-level services, as opposed to applications, really have to consider parallelism. And that's because if an application is going to fall over because it can't use multiple cores, you want it to be because the application had some sort of a limitation that prevented it from using more cores. You don't want an application that says, I can use 400,000 cores efficiently to basically run at the speed of one core simply because your system level module doesn't consider parallelism. Right? So you don't really have the luxury of ignoring parallelism anymore, but we'll discuss this a lot later. Okay, so in summary, what have I talked about here? We have a number of system-level modules that we're talking about the design of, and there are a number of concerns that you really need to pay attention to when you're looking at system-level code, system-level modules, as opposed to applications. We're going to be reading a ton of code within this class, and this should give you a framework with which to assess the interfaces and the implementations of a lot of the code that we look at. So some of these concerns include the managing and multiplexing of resources. A lot of this is part and parcel in isolating different clients, making sure that different clients have bindings to different sets of resources. This is, of course, related to name resolution and how we actually resolve to different resources for different clients. Of course, different clients can have different namespaces, so they can have disjoint sets of resources. And then, of course, we have to consider I/O and multi-core, therefore concurrency and parallelism. So think of this as a mental checklist for your interface and implementation evaluation when you're reading code throughout the rest of the class. Hopefully this was useful and gave you a perspective on how to think about system design. We will continue hammering away at this throughout the class. Have a good time. Talk to you soon.